Now, the axioms and the corollaries, they provide a set of rules for computing probabilities of events in terms of other events. So if you have, let's say, probability assigned to A1 and probability assigned to A2 and the probability assigned to their intersection, then you can compute the probability of their union. But how do you know the probability of A1? That's an elementary question. So what about the absolute probabilities of basic events? This means we need an initial probability assignment, which we call priors, prior probabilities. Now here, this, as you see, is an assignment. So this is a choice you make. Depending on the mathematical model you're using, what you do is you essentially pick a set of probabilities for elementary events or basic events, and then work on it to produce some meaningful results. As long as you obey the axioms and use legitimate derivations, your results will be correct, but within the domain you choose to model. So what this means is, um, depending on your choice of probability assignments, the usefulness of your theoretical results in the real world might have different values. So you have to be careful about choosing your probability assignment. And we are going to see a couple of random variables later on that we can use in modeling real life scenarios. Now, a probability assignment of particular importance is the case of equally likely, in other words, equal probable outcomes. Now, this is one which we see very frequently, especially when we deal with combinatorial events. And well, this is simple to understand. For instance, when you toss a coin, we assume that the outcomes heads and tails are equal probable. So we assign the probabilities 1/2 to each of the outcomes here. Because we do not have any reason to assign, let's say, 0.7 to heads and the probability 0.3 to tails. There is no reason to do that. Therefore, we assume that those two outcomes are equal probable. But at the end of the day, it's our assumption. It's an assignment we make. And in real life, it holds water reasonably well. So we use that. But in many other applications, that may not be the case. So in the case of equal probable outcomes, if the sample space is countable with the size of k, so in my coin toss example, the sample space consists of just two elements. If you, for instance, throw a die with 6 faces, then your outcome, your sample space will have a size of 6. Or you can give other examples. And each outcome has 1/k probability. This is called Laplace's principle. Okay, so when you have this situation, we can use combinatorial counting methods to compute probabilities. If you can define events in terms of combinatorial combinations, let's say, then you can compute probabilities easily in such cases. Here's an example. Let's say we toss 3 coins and we assume equal probable outcomes. Now, this could be a repeated toss of the same coin 3 times, or this could be that there could be 3 separate coins where you throw them separately and independently without one affecting the other. So there is no reason why we should assume the outcomes are not equal probable. So we are going to assume equal probable outcomes, which means heads, 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 tails, etc., up to tails, tails, tails. We have 8 possible outcomes in our sample space. Okay, so when the order is important, for instance, if you are using the same coin and tossing it 3 times repeatedly, the order you see, the outcomes might be important for your application. In this case, the probability you assign to each of these outcomes will be 1/8. But if you are interested only on, for instance, the number of tails in those 3 tosses, then your sample space should be 0, 1, 2, 3, because these are the possible outcomes. But in this case, you see, the outcomes in my sample space are not equiprobable, because, for instance, heads, heads, heads has probability of 1/8, but in my new sample space, that corresponds to the event 0. Okay. On the other hand, heads, heads, tails, or heads, tails, heads, or tail, heads, heads, these 3 correspond to the event 1 in the second sample space. Therefore, the probability of 1 and 2 similarly should have 3/8 probability. Okay, so even the individual outcomes are equiprobable. Sometimes, depending on the definition of the sample space, our events may not be equiprobable. In case of equiprobable outcomes, if the sample space is finite with a size of k, then, as we have seen, each outcome has 1/k probability. But if the sample space is uncountable, as we have seen the difference between countable and uncountable, we know what this means. We are dealing with at least intervals. In this case, equiprobable outcomes apply to intervals rather than specific points. Okay, obviously this relates to continuous domains and continuous probability theory. So we are not going to really go into this discussion, but you have to be aware of the limitations of our discussions here. We are going to talk about discrete probability, and we are going to leave continuous probability out of the scope of this class.